Okay, so last time we kind of left off in the middle of this, which was totally cool. We collected some kind of superfluous data, which is fun, you know, it's good. We're going to use these. I know these are actually the keys you guys had, but I think we were using this one down here because I had gotten them mixed up. And we were talking about measures of center. Measures of center. And I put center in quotes. And you'll see as we go through today more and more why I put center in quotes. It's extraordinarily multi-meaning. That's not a word, it's made up. It has many, many meanings, multiple meanings. And there were three that I wanted to kind of chit-chat about. And we started to chit-chat about them. So give me one of them and what its meaning is, or its implication, or what you think about when you hear that particular one. Go ahead, let me hear some key statistics. Some key stats. Love it! So we have the median. And when you think about median, what do you think of? What do you think? Michael, that's right. Go ahead, Michael.
It's like the middle number, the center.
Perfect. It's the middle number by location. Middle number by location. I'm going to put middle, maybe location. You have to put them in order for this to work. One thing the median doesn't care about is relative size. So for example, this is our data right here. And we found the median, I think our median was 3, wasn't it? It was that 3 out there on the end. That's the actual middle data point. I think it was 16 in. If we changed that 8 keys to 18 keys, would that change the median at all? No, because we did that little chop chop. Chop, 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 and we ended up at that number 3 over there. That was with JC, right? We did the chop, chop, chop. And if it was 80 or 18 or 800 or 8,000, it would get chopped off first, and it would pair up with the 0. So it doesn't matter how far out it is. It has no effect on the median whatsoever. And we'll come back to that. There's a reason why that's important. We'll come back to that today. Good, good. So the middle location when the data is put in order. I'll put that in there too. That's kind of important. And we're going to slap this down in 2 ways, raw and grouped, both of which I want to get into today. So a lot of that today, actually. I think we nailed the raw stuff pretty good last time. Good, so median for the raw data was 3. We haven't done the group data yet, we'll get to that today. Another one. Another measure of center. Oh, the mode! What's the mode? Tell me about the mode. The mostest, that's right. I'm glad you guys remember that. The mostest. Most frequently occurring. What was kind of fun? Oops, I wrote most. Mode. Mostest. What was fun about your data sets, mode?
You had 2.
You had 2, which was very, very cool. You almost had 3. There were 7 4s and 7 2s, and there were 6 3s. You almost had 3 modes. Kind of cool. And some statisticians would actually call that 3 modes. But we made a deal, I think. And the deal was we only count the ones that occur the most. So we're going to count 2 and 4 as the modes. It's beautiful. And the last one we haven't talked about yet. The mean or the average. You're all right. I'm going to use the symbol X bar if that's okay. Just because that way we're all talking about the same thing. It's the arithmetic mean, it's the mean, it's the average, it's the arithmetic average, all the same thing. And this is the only computational one, really. How do you find that bad boy? Yep. You add up all the data and divide by how many there are. And our average was what?
3.2.
3.2. What was the sum, friends?
99.
99 out of the 31, yeah? Which is your 3.2. Beautiful. I want to come back. The reason I want those 2 numbers for a reason. What do we think of when we think about the average? What does that 3.2 represent? Good! The fair share. I like that from last time, Skylar. Yes, the fair share, Hattie. And what does that mean exactly? Thank you, JC. If together we have 99. Perfectly said. If together as a class we have 99 keys, if we split them up equally, everybody gets 3.2. Fair share, everything's equitable that way. Yeah, I love that fair share. It's the first time I've heard that particular description of it. I love it. There we go, fair share. So you got an X bar, which is your average, You got your median, which is your middle location, and you got your mode the mostest. Beautiful, beautiful. And I think we can handle raw data now. I think we've got a pretty good lockdown on raw data. Problem: very rarely do you get it. Here is the problem with raw data is that it's often hidden from you in research. And oh, can't really see that. Let's scooch over here so you can. That's better. Beautiful. Very often in research, you're going to get this instead. That's going to be your data given to you. And the reason for this is people that, when vast majority of you are going to be consuming statistics rather than doing statistics. Some of you will be. Some of you, besides talking to 244 students, that they're running a 370 and 371, and chances are they're going to be doing surveys in the woods, doing inferential stat. Totally awesome. But for every one student like that, 5 are going to be just reading journals and being able to collate results from journals and come up with alternate solutions or reciprocal solutions. So this is what you're going to get very often. And it drives me nuts. I think I told you guys about the energy bracelet thing, right? The energy bracelet? No? You didn't say about that? So energy power bracelets, you've maybe heard of those? Power bracelet? Yeah. Right, put the power bracelet on, all of a sudden you become Charles Atlas. So it was this great study. There was an ad for the, you can Google, you can YouTube it, it's hilarious. This is a dude, you know, in like a really tight fitting shirt, totally buff, and he's trying to advertise this thing called the power bracelet, which is supposed to increase your athletic effectiveness. And he's got this skinny dude with him, and he's like, dude, jump! And he makes the guy do like a standing long jump. And then he's like, now put the power bracelet on! And he puts it, and once the guy jumps, and he jumps like 12 more feet, because this dude's yelling at him, first of all. Second of all, he had a practice run, so he knows what to do, so he can do it better the next time. And it's patently ridiculous. And the bracelet's a piece of rubber with like a piece of metal inside of it or something, and it's supposed to harness your chi in some way. It's complete garbage. Not that chi is garbage, I'm not saying that. I'm saying this bracelet harnessing your chi is garbage. So anyway, a statistician tested it. What they did was they got a double-blind study going, where they made a bunch of bracelets that looked just like the power bracelets, and then they bought a bunch of power bracelets. And the double-blind study, they recruited people to come in, and they flipped a coin behind this curtain. And if it came up heads, they handed a power bracelet to a researcher who didn't know what they were getting. So the first blinding is the researcher had no idea what bracelet they were picking up. The second blinding is the researcher then put that on the wrist of the person in the experiment who also didn't know. There's your double blindness. And then they were told to, please jump from this line to as far as you can go. All right? And they probably even let them do it a few times before putting the bracelet on, just so there was no practice involved. There wasn't a practice. It was an uninterrupted momentum. And then they went back and switched the bracelet. Researcher, assistant, and the subject still doesn't know what they're getting. And they kept track if there was any difference from one jump to the other with or without the power bracelets. And lo and behold, guess what happened? There was no difference. There was no difference. I would kill for that raw data. And the guy that did it will not give it up yet, because it isn't published yet. He's still working on getting it published. And I was like, I'd love to see it. He's like, you will see it when it's published. And when I see it, it'll look like this. I want this. I want that. I won't get that. I'll get this. So, since we get this in the journals, we better figure out how to deal with it. And we dealt with one of these yet last time, didn't we? Didn't we pull one of the measures to center off this? Hattie, which one did we get?
Mode.
We pulled the mode. And why was it so nice to pull? Because it's the most, just go to the bar that's the biggest. Go to the bar that's the biggest. The bar that's the biggest is 3 to 5. Now notice there's some skew to this distribution. There's quite a bit here too. That's because there were so many 2s. The 2s and the 4s drove both of these bars very high. But we're going to go with this because we're going with simply the one that is the tallest, which is at 16. So you can either put 3 to 5. If you want a single number, just call it 4. If you want a single number, just call it 4. Use the number in the middle for the most part. Cool? Easy enough? Did we do any others, or was that it for that was all we did for Tuesday? Good. Well, let's get some other ones. Which one should we do next? Median? Do the median next? Okay. How? Remember how we found the median with the raw data last time? What do you think, Kate?
Well, you could do it kind of the way
Please.
that we did it yesterday.
Please.
I don't know.
No, you don't have to.
Do it?
JC, get back up. You're my go-to now.
Well, you know that between 0 and 2, it happened 12 times. So pick 0, between 0 and 2, random, doesn't matter what number you choose, in order 12 times. And then the same for between 3 and 5, 16 times. And between 6 and 8, what is that, 3 times? And then cross it off that way. You won't know exactly the number.
I love what you just said. You're actually describing the average justification better than the median. Can we come back to that?
Okay.
Thank you. It was totally freaking awesome, by the way. We're going to come back to that. We're going to come back. You actually justified why the average works.
Well, it would work for the most
But
if you cross
it works. Here's why we don't need to go into that much detail for it. Okay, you ready? Ready, JC? How many we got here, friends? 3. I'm going to chop off the biggest one. JC? You're going to chop off one of the smallest ones. Well, you see how there's 12 here?
Yeah.
So technically speaking, each one of these is 1.
So just like.
Yeah, there you go. Boom. Good. You took off 2. I'm going to take off 2 as well. Okay, so now I have 1 left. So why don't you take off 1 more?
So just.
Yeah, there you go. There you go. So that's 2. That's 1, 2.
Oh.
So now there's 3 and 4. Let's just do it this way. This may be clear. Let's do it this way. That might make it easier for you to see. So there's 12 little triangles in there. That represents the 12 that are in that.
Let's do it for this one too, right?
She's on. She's on. That's what JC's go-to. There you go. So what I'm going to do is I'm going to chop off my 3, and I've got to take 3 of hers off, correct? You see what I'm taking? When I say hers, I mean the far bar. This is equivalent to what she and I did on Tuesday, where you chop, 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 chop. We chop the high, chop the low, chop the second high, chop the second low. Excellent, my friend. Sorry about the bar in the middle there. It's kind of annoying, huh? Beautiful. Look at that. So there's 16. So I took off 3. You go ahead and take off 3. So now the top's gone. Okay, so now I'll go to here and you go to there. So I'll take off 4. Let's just do 4 at a time. Can you knock off 4 of yours? Beautiful. I think you want to need that guy too.
1, 2, 3.
Right, but you got this one in the first one, right? Beautiful. How many you got left? You got.
1, 2, 3, 4.
Take them all off. We're going a little out of order, but we're keeping track of it. Now I'm going to take 5 off. 1, 2, 3, 4, 5. And now, go ahead. Yeah.
There's 7.
There's 7, as there should be. There should be an odd number, right? Because we had an odd number of data points. So we're going to take off 3 and 3. 2, 3. So there's our median. Technically, that triangle right there. Now, the problem is I don't know what data point that is because it's in that bar. So what do I call it?
3 to 5.
You call it 3 to 5 if you need one number?
4.
Call it 4. Boom. JC, thank you again. Go to. Boom. That's it. Call it 4. Now, did you see, past the point, we didn't even have to, once me and JC got down to all 7 being in the middle bar, we didn't actually have to chop 3 and 3 anymore. I'm glad we did. That was a great visual to do it that way. But we didn't have to, because if we chopped all those, we're still going to be in that bar. So essentially, once you chop down to, and you're into a single bar, your median's in there. There are formulas that some textbooks teach you. Since ours was down closer to the bottom of this bar, they assume it's closer to the bottom of the range than the top. So they might say 3 or 3.5, which would actually agree with our true median of 3 on the raw data. I say don't worry about that because technology does those formulas for us eventually. So don't sweat formulas like that. They're not worth memorizing. Is that fair? Kate, I love what you said. We're coming back to it, I promise you. I promise you. You don't like what?
It's not accurate. I don't like it.
Well, but the problem is, friend, you're only saying it's not accurate because you've already seen the raw data.
I know.
You're not going to see the raw data most of the time. That's what you're going to
I
have.
want to see the right.
You want to see the raw data? Well, hell, I do too. But I also want world peace.
Well, then go make one.
Then go make world peace.
Go do it.
We'll have a cup of coffee so I'm talking about why we can't do that. We'll have some more cups of coffee and try to do it. Okay, we got median taken care of. Now, I want to get back to, okay, thank you, JC, that was perfect. That's perfect.
Yeah.
I want to come back to Kate's point. I love what she was saying about spreading the data through the bars. We got one last thing to talk about now. And the last thing we got to talk about is the average. How are we going to get the average out of this data? What do you think? When I say average, I mean the fair share. Skylar's fair share. How are we going to get that out of there? What are we thinking? This is Cameron, right? Harrison. This is Harrison.
When you add up all the points, so 12 plus 16 plus 3, right?
That's going to give us what? 12, 16, 3. It's 31.
31.
That's how many we had. Beautiful.
Right?
That's part of
You
it.
add up. Would you take like from 0 to 2, we should say 1, 4, and 7,
Okay?
and add those together and then divide them by.
I love this. I love this. It's hitting what you're before, Kate. That's what you're saying. So what Harrison says is, okay, I know there are 12 data points in this range. I don't know what they are, but they're between 0 and 2. So Harrison has a vote to call them all 1. I like that. It seems to make sense, right? It seems to make sense. We'll come back to why. Kate was getting into why it makes sense. These we're gonna call all these 4s, and those we'll call 7. But then you said, Harrison, you said to add up the 1, the 4, and the 7 to get 12, and divide it by 31.
Yeah,
The only problem with that is that's 12 divided by 31, which is roughly a third. Is that close to our true average of 3.2? So Harrison, I think we can see what we have to do if we write down what you just said, kind of chartily, if you will, like in a distribution. Check it out. I'm going to slide over here. Harrison, you're saying the right thing to do, brother. Actually, I'm going to go right there next to it. I'm going to slide this up. Everything you said, we got to do. But there's one extra thing we have to do, too, to make sure units agree. The problem is the units aren't agreeing. And here's why. Here's why we're going to figure it out right now. Okay, so, and that doesn't really help, there's lines there. Just mute it then. Ooh. So, I'm going to make an X column and an F column. This is like the distributions we talked about last week, where you have your data, and when you don't have raw data, you've got a second column, which is how often to count the data. So, what Harrison is saying to do correctly, I might add, is put 1 and 4 and 7 in here. And what we call those are usually called class marks. I think your book calls it that, at least most books do. And all they are is the middle value of whatever your range is. So if your range is 0 to 2, it's 1. If your range is 0 to 3, it's 1.5. If it's 0 to 4, it's 2. Just take the halfway point. And sometimes it's a decimal, and that's totally fine. That's totally fine. Okay? And the frequency becomes however many there were. And I think that was 12, 16, and 3, if I did that right in my head. So this is how many. Beautiful, beautiful. And then Harrison says something else. He said, add up the 12 and the 16 and the 3, and get 31. And if it's okay with you guys, I'm going to use that symbolically. I'm going to use that big sigma that we talked about last time because I like him. Big sigma F, which is the summation of all the F's, which is 31. And what does that tell us again? What does that number tell us again? Yes, it's sigma F. But what does that stand for? Go ahead, Hattie. The sum of F's. And what does that stand for conversationally? If I had to explain that to a non-statistician, what would sum of F imply?
Add them together.
Right, add who together? Or what together? Right, that's what I'm after. It's the people in my sample. It's the people that were in the room on Tuesday. Yeah, add up, you're right, yeah, of course. Add them all, add the F's together, how many there are. But what are the F's representing? It's how many people were here on Tuesday when we did the experiment. Or I guess it was last Thursday we did the experiment. So that's conversation. I like having you guys say things in non-statistical language too. So when you have to explain it to your friends who get the Facebook post that says, you know, Elvis really isn't dead and here's the stats that prove it, you can explain to them that, yeah, sorry. And you have to go to explain it in non-statistical terms. Sorry, I don't want to pop it in my head. Good. Now the problem was, if we add 1 and 4 and 7 to get 2, otherwise, that looks like the sum of X, doesn't it? It's not Y, Harrison. Oh, wait, who's next to you?
Heather.
Heather, tell me why, Heather.
Oh, no, I had something else.
You had something else, tell me.
No, but if you take 1 times 12 and then 4 times 16, 7 times 3, and then...
Why do we have to do that, Heather?
Because that's how many there are averagely.
Good. This is a number of keys, right?
Yeah.
And this is how many people had that number of keys, Harrison. So, Heather, what you're saying to do, if I may, call it XF.
Yeah.
X times F. So 1 times 12 gives me 12, which would mean what?
There were 12 ones.
There were 12, good, and those ones are,
Got 1 key.
each of those 12 people has 1 key, so there are 12 keys for those people. Good. Next one down is 4 times 16, that's 64, which would mean that there are 64 keys for those 16 people, and next down will be 21, yeah? There we go. Love it so far. Love it so far. Looking great. Looking great. What are we going to do with those numbers? Okay.
Add them up.
Then we're going to add up,
And
huh?
divide by your overall 31.
Thank you, my friend. Thank you all three of you, you put the average together, just those pieces. Add them all up. Summation of XF. Summation of XFs is going to be 12 plus 64, what's that, 97? Did I do that right? Kate, you said you hated...
This one actually is really close.
No. She's changing,
I did it.
She's changing her tune all of a sudden.
No, I don't like the other.
Now, hang on, hang on. Hang on. You gotta make peace with this, sister. You gotta make peace with the fact. Did anybody else? 97. How many keys were there in the room? 99! We were off by a couple percentages of what it would actually have. This is the raw data, that's what actually was there. But by doing it via groups, we end up with the summation of XF over the summation of Fs, which is 97 over the same 31. The 31 is going to be the same because we're counting it by the same number of times. Well, is that drop to 3.1?
Yeah.
There we go. We'll call it 3.1. I can tell you this. I've been doing this experiment for 18, 19 years now, multiple times a year. I've never been off by more than 0.3 from the true value. Wow. There you go.
Sorry. To include outliers, like so say you've got like 7 janitors in a room, right? And some dude's got 27 keys and...
Can you hold that thought?
Absolutely.
Thank you, because it's a fantastic, and I have an answer for it.
Okay.
Only because I was interested in the exact same thing. Just hold that thought. We'll come back to it. Give me 3 minutes, maybe. The reason I'm making a big deal about this is twofold. Number one is the fact that you can actually do something with group data. Yes, Kate, I agree. I would rather have this. But in lieu of having that, I have this. It's kind of like instead of having world peace, I'll settle for the pond with water features in the backyard. Because I get that sense of serenity. Maybe not worldwide serenity, but localized serenity. This is my localized serenity. And it's close to that feeling I want to get from world peace, if you will. So I can do something with it, and more importantly, it's accurate. And here's why it's accurate. And I'm going to make a YouTube video for this for you guys for tomorrow. I want to use an Excel spreadsheet to explain this better. But Kate was hitting upon it. When we had this histogram that came at you, all you know is that there are 12 data points from 0 to 2, 16 from 3 to 5, and 3 from 6 to 8. You don't know how many there are. So what did you assume? That all of these, Harrison, were what?
1.
Yep, 1. All of these were?
4.
And all those were?
7.
Now, what assumption that really makes is what Kate said. And that's that there are the same number of zeros, ones, and twos. So basically, within each bar, they're evenly split. So there are 4 zeros, 4 ones, and 4 twos. There are 5 1/3 threes, 5 1/3 fours, and 5 1/3 fives. And there are 1, 2, 1 of each, 6, 7, and 8. Now we know that's not, Michael, go.
Well, you could find a range of correction and incorrection by doing all 0, 3s, and 6s, and then doing 2s, 5s, and 8s, and you could find the min and the max.
Brother, 100% correct. The problem is you can't, this is what you're stuck with.
Right.
If you had more information, yes, but this is what you're stuck with. This is that same problem we had yesterday, or whatever it was, Tuesday, with that histogram where the bars weren't the same width. I would love to correct them so they were, but we can't because we don't know. If the bar is $25,000 wide and 2% of Americans think that, that doesn't mean that 1% think it's in the bottom half and 1% think it's in the top half. It just means that 2% think it's in that entire range. See what I'm getting at?
Yeah.
Does that make sense? But there's a problem, as Michael has pointed out. When I go back to the raw data, in that first, there should have been 4 zeros, 4 ones, and 4 twos. Well, there were 2 zeros, 3 ones, and a whole buttload of twos. Right? 7 twos to be exact per our mode. That's a problem. So we horribly overestimated, or excuse me, we underestimated the first bar. We thought there were more zeros and ones than there actually were. With me so far? Then in the next bar, we assumed that I think there were 5 3s, 5 4s, and 5 5s. But you see what we did there? We overestimated the second bar. Because there were only 3 5s, we thought... Say it nice and loud.
Cancel out.
That's called the law of large numbers. What happens over an entire data set is you overestimate some and underestimate some. And it all washes out at the end. That's why I told you over 18 years of doing this 3 and 4 times a year, I never get more than 0.3 from the average. Because this always happens. Because I have yet to see a data set where it's all 2s, all 5s, and all 8s. Could it happen? Sure. It totally could. It just never has. And every year that passes and it doesn't happen again, I tell myself, it's probably not going to happen this year either. Let's just see what happens. So what I've done, Hattie, slide this back over here, is I have kept track over time. That is the historic, including you guys, the historic occurrence of keys in this class. And one time, a dude showed up with 29 keys.
Why?
What? I don't know. You wouldn't tell me. I'm like, dude, why do you get so many keys? He got a little nervous and left.
He was a janitor.
And he got nervous and left. I don't know why he left, but he was right. It was at the end of the day, just like with you guys. And I just, anybody got more than whatever it was, 10? And he puts his hand up, I'm like, what do you got? 12, 13, 20? I think it was 29. Holy hell. Why do you have so many keys? And he just left. I think he dropped my class. I never talked about that. Whatever, it doesn't matter. But the fact of the matter is, this is what the distribution of the population is looking more and more like. Right? Could we find the mode, the median, the average from this? Of course you could. Of course you could. Where's the mode? Where's the mode?
3 to 5.
Shoot, it's 3 to 5, just kind of like it was for our group data of 4. Where's the median? JC, get back up here. I'm kidding. I'll get back up here. But could we do what, could me and JC do what we did before? Yes. A matter of fact, this is cool. I didn't realize this until yesterday. We actually wanted to do it in yesterday's class. These bars add up to that one exactly.
Oh.
Which is very, very slick. So we would do our crisscross, and that would exactly cross off 212, which means the median is right in this bar as well. Now, Hattie, your question, which was a fantastic one, where's the average? Where's the average? You mentioned a very special word a few moments ago.
Outliers?
Uh-huh. That guy. That guy. Why?
Because it doesn't follow the rest of the data points, and it doesn't represent the rest of your data points. correct?
That is a good reason to do it. That is a very, very good reason. There are things called outliers in statistics. We're going to study them more rigorously as the course goes on. One definition of an outlier is a data point that does not represent the remainder of your data. For some reason, it's very, very, very different. One thing you can do with it is toss it. If you toss that outlier, we'll come back to this in about 10 minutes, but let me ask my first question. Where's the average of this data set? What, if you had to get, I'm not going to make you calculate. I'll make you calculate some other weighted means today. But where would the average be? 3 to 5. Go for 3 to 5. Okay? I'm going to throw one more word in for average besides fair share, which I love. But I'm also going to throw the word in balance. The balance point is where an average also is. The balance point. Check this out. I'm going to back up to our graph. There's our graph. Now, if you had to balance this histogram on a single point, would you put it right there? Would that balance? I don't think so. I think there's too much weight on that side over there. I think you'd have to slide it closer to this side. Somewhere in here-ish, wouldn't you? In order to balance it. And that agrees with our calculation, doesn't it? Because when we calculate our mean to be 3.1, right about over here now, isn't it? So a balance point is where your average actually lies. It might not be the median balance point or the modal balance point. It could be. Doesn't necessarily have to be. So where do you think, knowing that, where's our balance point here? I'll tell you what, I'll start and you tell me where to stop. Going forward?
Yeah.
My gut is more like here. Because of the 29.
Oh, yeah.
Remember, he's way the hell out there. And the further out he gets, the more this has to go over to counterbalance that. Think about it. You're on a tightrope, perfectly balanced, and somebody drops a can of Pepsi out on the end. What do? You got to adjust for that. That's what the average is doing. The median's like, dude, whatever. I don't care. But the average has to adjust for that. It has to move to counterbalance that Pepsi can. Please, Michael.
But it's not going to move that much because there's only one person with 29 keys.
That's why, brother, that's why I didn't go all the way over to here. I said I think it's going to be a little bit more this way. I don't know how much more, a minor percentage more. But the idea is the average will chase that outlier. You're right. It's only 1 out of 1,000, roughly. Not very much, Harrison. Thank you, Michael. Harrison.
Wouldn't the law of large numbers cancel him out?
How would it cancel him out? Actually, we call him 28 is what it would do.
Okay.
He's there. So you can throw him out by... Don't confuse the law of large numbers with an outlier. He exists. He is a data point. That bar, by that bar, he's a 28. because on average, he's in the middle of the range. So all these are 1s, all these are 4s, all those are 7s, all those are 10s, and so forth and so on. Law of large numbers doesn't cancel, it just places, if that makes sense. And I'm going to have, I think if this video I've got in my mind to make for you guys, I think will clear that up pretty nicely. Is that fair? Great question, fantastic question. It doesn't cancel. Dealing with outliers does cancel. Now, Kate, I got one more thing to have you think about outliers, not just Kate, everybody. Outliers aren't always bad things. They're definitely unexpected things, but they're not always bad things. For example, polio vaccine, okay? HIV cocktails. Why do these things exist? Why do these things exist? Why does any drug, aspirin, Advil, Sudafed, Viagra for that point, why do any of these things exist? Don't be too descriptive on the Viagra. Why are any of these drugs sold? Matter of fact, I heard Viagra was actually supposed to be, it was designed to do something else, like heart medicine, and they're like, oh, look at that. Anyway, why are these drugs sold? Kate, go ahead.
Well, just thinking from the medical, okay, so you have a problem, and you're like, crap, we need to
Fix this
solve
problem.
the problem.
Remedy this
You're
problem.
going to start working with a whole bunch of things, and your chances are most of them aren't going to work, but your outlier is going to be the one random antibiotic or something that does work.
Or maybe it's not random, maybe we wanted that. Here's the deal, right?
And you just weren't expecting.
Awesome, you weren't expecting it, or maybe you were hoping that it would work, and that's the data you need to prove, quote unquote, that it works. So suppose this is circulation for those with clogged arteries because of high cholesterol. So this is what the typical is. And it follows a nice curve, a nice predictably shaped curve. And you create a drug that's supposed to help with circulation, and that drug comes back. The one person on that drug, now it's not going to be one person, it'll be a whole sample of people, but their average circulation comes back over here. So maybe their curve looks something like this. Do you think that's a different curve than this curve? Yes, that's the outlier curve. Now in that case, you don't throw the data away, you keep it and you say, my drug looks like it's working.
It depends on what your data is, however. So
Oh God, yes, and this is 244.
So
We're getting
like,
into 244 discussion.
yeah, so
Stop.
Stop. But you're right. It depends on how far away, the margin of error, all kinds of things that we're going to get into in 243. But that you don't. I guess my point is you don't always throw outliers away. If they're miscalculations, if they're non-representative and you can prove it, you toss it.
or what you're looking
Oh, be careful. We're starting to toe the line now. All right, you're getting a little punchy over there, Kate. Let's take our 5. Get that glazed look too, anyway. Walk out of here, get some air, get some water, come back in. I want to talk more about this.
for. So,
Good for you, sister.
my way